Energy and matter. I mean, matter and energy. Okay, so chemistry is basically the study of matter. And everything has matter. So we talk about matter. There's kind of scales that we kind of set up in terms of science. So we have what we call the macroscopic scale. Macro meaning big, like the Big Mac. You guys are familiar with the Big Mac? Micro meaning small, meaning that we're going to need a microscope to see it. And particulate meaning it's so small that you can't even see it with a classic or a normal microscope. Okay, you have to use specialized microscopes to see it. Okay, so down here is pretty much a scale, and it gives you an idea of what we're able to see. So macroscopic, we're able to see with our eyes. Microscopic, we're able to see with a microscope. And a particulate, we need specialized microscopes to actually see it. Okay, questions, concerns? Cash? No cash?
I wasn't able.
Okay, so let's start this out. Ms. Perez, how are you doing this morning?
I'm good. How are you?
I'm great. So can you tell me something that is macroscopic?
Macroscopic, that would be like boulders, mountains, and cliffs and things like that.
That's beautiful, yeah. Those hills, the boulders, mountains, and cliffs, that would be macroscopic. Let's see. Hugo, can you tell me something that is a particulate?
The hydrogen atoms.
The hydrogen atom. Nice, nice. Okay, Fabian, you have microscopic.
Something that's microscopic?
Microscopic.
It'd be like oxygen atoms?
Oxygen atom, that would probably be a particulate, because we're going to need a specialized microscope to see it. Something that you're going to use a classic microscope.
Well, probably like the cells and
like a cell, exactly, just like a cell. Okay, so you want to have an idea of what we're working with. So we're working with atoms. So can you guys see the carbon atom with your eyes? You can respond.
No.
Yes, no, maybe.
No.
No.
No, you can't, right? And if you could, you have incredible eyes. You put Hawkeye to shame, right? And we don't have that type of vision. So when we're working with things at this scale, we're going to have to use models, right? So if you're looking at a compound, if you're looking at a single molecule of sugar, you can't see that with the naked eye. So we need to find a way so that we could manipulate the structure and kind of understand the structure for our well-being. And the way that we do that, got carried away. We use a model. So there are two types of model. We have the stick ball model, and we use the space filling models. Those are the most common ones. So this basically is methane. Have you guys heard of methane before?
Yeah.
Yes.
Yeah. Where is methane mostly found at? Particularly in this area or in the Kalinga area.
Cows.
Cows. Oh, what about cows? How do they make methane? Where is that methane coming from?
Their feces.
Their farts, actually. So their feces and their farts. So cow fart is primarily methane. And if you guys are living close to Kalinga, around 8 o'clock at night or so, something like that, you get this big, huge whiff of methane gas coming through the town of Kalinga because they just got through eating and they digested their food. And so it's a real lovely smell. Am I wrong?
Oh, it's great.
It's great? Yep. Yeah, so we all are very familiar with that. So we know that cow farts has methane. So this is the chemical structure for methane. Methane consists of C, which stands for carbon. It has 4 H's. Each of those H's are a hydrogen, right? And it's in a tetrahedral structure. We'll talk about that later, okay? So this is the chemical composition for methane, CH4. This is the structure, drawn structure on a piece of paper so that we can sit there and share the information with each other. This is a ball and stick model. Why do you think it's called ball and stick model? Tim?
Because there's balls and sticks on that model.
Because there's balls and sticks, right? Makes
Right.
sense, right? Okay, so we use a ball and stick model to help us understand how that structure is. And it's important for us to understand structure because that helps us figure out what type of reaction we're going to get, where things are going to be placed. It's going to be very relevant in the world of chemistry. So you want to kind of pay attention to that ball and stick model. Okay, so the space filling model, same thing. Now here, and it's typically traditional, hydrogen is going to be white, carbon is going to be black. That is not racial tones or anything like that. It's just hydrogen is white, carbon is typically black. And so often in your drawings, you'll see the ball and stick model where all your hydrogens are going to be white and your carbons are going to be black. Okay? Questions, concerns, Cash? Okay. Oxygen is typically red, and then your halides, we'll talk about in a minute because you probably have never heard of a halide. Those guys are typically green or yellow. Okay, so because we also are working with chemicals and we're chemists, we don't want to write down for methane, we don't want to write down carbon, the full name carbon, and hydrogen. We want to just use symbols. So we use that C and H4, okay? So we use symbols to represent the different atoms. Those symbols can be found on your periodic table. 1 second. P table is where I like to go for my periodic table. We've kind of discussed this, did we not? P table? Yeah, we talked about P table, right? So H stands for hydrogen. It's written right up there. B stands for boron. C stands for carbon. So if I write something like this, what is that symbol?
Calcium.
Calcium? Is it really? They're both lowercase. Are you sure?
Yes.
Calcium.
You're sure?
Yeah.
No, it's wrong. It's nothing because they're both lowercase. Okay? So they're written the way they're written because we want to be sure that we understand what we're talking about. Like, for instance, if I write can you tell me what that is?
Boron, sulfur, whatever A is.
Okay, so we would assume it's boron, sulfur, and whatever A is, right? But there's nothing that has A, right? So I would immediately say somebody didn't know what they were actually writing, and I'd mark it wrong. So if I'm writing for boron, of course, boron is B. If I'm writing for barium, it's capital B, lowercase a. Do you guys understand what I'm trying to get at? And I know that some of you guys, your handwriting, you write everything in lowercase, and sometimes you guys write everything in uppercase. So you don't want to do that because it's actually wrong, because then we won't know what you're talking about. Okay, so what is the chemical symbol for chlorine? You guys can use my board, right? Everybody can write on my board?
Yeah.
Can you find chlorine?
Cl.
Cl. So how would you write it? Write it on my board.
Okay, let me see my pen.
Okay, polonium. Carbon. Okay, simple. You guys get it? Okay, so if I have this, what's that?
Nothing.
No, it's actually something. It's actually carbon monoxide because it's carbon and oxygen. Okay, but this is
Carbon. No.
Cobalt? Wait.
cobalt.
Cobalt.
Cobalt. Okay, you got it? Now you see the relevance of that uppercase and that lowercase. I know it seems simple and you're like, God, he's acting as if we're in the first grade. But 99% of the students on the very first exam will get points deducted because of this. Okay, so we use symbols to sit there and represent the chemical that we're talking about. And that's going to be important because it'll allow us to do a lot of work in a short amount of time, and we don't want to write novels. We like brevity. We like it to be brief, short, and to the point. Okay. Okay, so for instance, we have water. So we don't write out water, we just write H2O. And that lets us know that there's 2 hydrogen and 1 oxygen for water. Okay, simple, not too hard. Okay, great. So since we know about water, you guys know about water? You guys drink water?
Yeah.
Okay, good. Now that you know that you drink water, so what are the different forms of water? Or the different states of water?
Water, gas.
Steam, liquid, and then ice.
Solid, ice.
And steam
Solid, liquid, gas.
when it's a gas.
So the 3 different states are solid, liquid, and gas. We call the solid what?
Ice.
Ice,
We call the liquid what?
water,
Water.
And we call the gas what?
steam.
Steam.
Okay, so I'm going to ask you a really hard question, and I want you to think about this. Think really, really hard, okay? So, chemically, is ice, water, and steam different from each other?
No,
Then how are they different?
the molecules are slowed down. They don't move as fast in each state. So when it's moving really fast, it's a gas, right? Steam. And then if you slow it down a bit, it becomes a liquid. And if you slow it even more, it becomes an ice.
Okay, so it's movement, right? Thank you, that's great. I didn't have to do my little dance for you guys. That's okay, so kinetics. How many of you guys are in kinesiology? Or planning to be to go into kinesiology? Anyone?
Yeah.
Yeah. So if you're in kinesiology, what does kinesiology mean?
Is the study of movement.
It's the study of movement. So kinetic means movement, right? So kinetic molecular theory means movement of molecules. So it's the theory of movement of molecules. Okay? So like you just told me, if it's a solid, it's really tight, it's not moving too much. If it's a liquid, the molecules are moving a little bit more, right? And if it's a gas, it's popping off the walls. It's moving like crazy, okay? Simple? Okay, so what causes that movement? How does ice become water? How does water become steam?
Change in temperature.
The change in temperature. By us changing temperature, we're putting energy into that system, and we're causing that shift from one phase to the other, or from one state to the other. Okay, so how many of you guys have been on a hot beach? Stands real hot. What happens? Do you just sit there, standing still?
No.
No.
What do?
Water.
Run to the water.
You run to the water. Do you run pretty fast if the sand is really, really hot?
Yes.
Yeah.
Okay, so that's just like these molecules, right? The hotter things are, the faster they speed up. So it's that same concept. Simple?
Yes.
Good. Okay, so we've talked about gas, liquid, and solids. Now there are two types of solids. One is really organized, and one is a hot mess. Okay, so the one that's really organized, we call that a crystalline solid. It has a very defined pattern, very defined, it's arranged perfectly. The other one is called an amorphous solid. How many of you guys are sci-fi fans? Anybody like sci-fi movies?
Yep.
Okay, so what is a morph? Morph, just a morphling or
Where they change.
change, right? So amorphous or change of shape, typically, right? We associate it with them being able to change shapes, right? So amorphous, A means lack, morph, change. So it lacks change, or in other words, it's a hot mess. It's unorganized. It doesn't have that order. It lacks order. Okay? So those are your two types of solids. That'll be important later on, but you still kind of know a little bit. Okay, so.
Wait, I'm sorry. What was the other one? It was crystalline solid and what else?
It's
Amorphous.
crystalline solid and amorphous.
Okay.
And all my lecture notes are available under modules.
Okay.
So we have a gas, liquid, and solid. So a gas, does that have a defined shape?
No.
No. It just takes the shape of the container. It just spreads out as big as that container is or how small that container is, and that's it. What about a liquid?
It's the shape of the container.
It's the shape of the container, right? So it's in this bottle. Guess what? It's the shape of the bottle up until the point that's full, right? What about ice?
Yes.
As shape.
Okay, so it'll be rigid, it'll be fixed, it'll be constant based upon what we molded it in, right? When it was water. Okay, so if I have a little heart-shaped ice cube, it's going to be a heart-shaped ice cube, right? But as soon as I melt it and I put it in a cup, it's going to be that shape of that cup. But if I put a heart-shaped ice cube, it's still going to be a heart-shaped ice cube. Okay, now the volume of water, is that constant?
Yes.
Yes. Okay, so yeah, the volume of water is constant. So if this is 500 milliliters, then this is 500 milliliters of water. That volume isn't going to change. What about my volume of ice? If it's taking up, let's see, 500 cubic centimeters. If it's 500 cubic centimeters, that volume isn't going to change. Now gas, on the other hand, it's going to be based upon the volume of the container, right? Because it's popping off. It's constantly moving around there and it's just going everywhere. It's just going to expand until that volume of the container contains it, okay? So we've already talked about movement. So which state does the molecules move the fastest?
Yes.
Yes.
Okay, simple. Okay, so we've already kind of talked about this, right? But let's put this in characteristics of, is it a chemical change? If we're going from a solid to a liquid to a gas, is that a chemical change or is that a physical change?
Physical.
Physical.
Everybody agree?
Yes.
Okay, why is it a physical change since you guys all said it's physical and plus it's on the board?
None of the chemicals are changing. I mean, sorry, the molecules.
None of the molecules are changing. It's still, the chemical composition is H2O. It hasn't changed. It hasn't split up. It hasn't broken apart. It hasn't done anything, right? It's always going to be H2O. So there's not a chemical change. Now, I'm going to ask you a question. I want you to think about it. How many of you guys have tried to make caramels or candy? Anyone? Yeah? Okay. So I tried to make caramels and candies. I put my sugar on the stove, right? And just started out with the sugar, started cooking the sugar. And at the same time, I'm trying to grade about 50 papers. And so as the sugar is, melting and everything like that, I'm just typing it up and, doing what I'm doing. And then I smell smoke. Kitchen is like all fogged up and things steamed up. And then I get there and my sugar is pitch black, right? Is that a chemical change or is that a physical change?
Physical change.
Chemical change.
Chemical? Are you sure? You're supposed to say yes. Are you confident? Be confident, okay? Yes, it is a chemical change. So if I put my table sugar is called sucrose. It first caramelizes, it turns brown, turns a brownish color. That's the first sign that we're actually starting to get a chemical change because you're having a color change. So often we can define chemical changes by what's happening. The next thing that happens, we get steam coming off of it and it starts to turn black. So that black means that we're breaking down the composition of sugar. And let me give you the chemical composition of sugar. So that'll make a little more sense. So this is C12H22 O11. So that's the chemical composition for sucrose. So what happens is we break it down to carbon and water. When we burn it this much. Okay, so in this case, we've broken it down. And this here represents a chemical formula or a chemical reaction. Sorry, not a chemical formula. This is a chemical formula. This here is a chemical reaction. This here, this is your reactant. It's what we're putting in initially. And this here is what I end up producing by accident. This is my product. This here is one molecule. This here is one element. So what you have on your periodic table, those are elements, okay? So we've broken it down to 12 individual elements of carbon, or 12 individual atoms of carbon. Here we have 11 molecules of water, okay? And at this point, you should be asking me, elements, molecules, atoms, what the hell is he talking about? So we need to make a definition. What is an element? What is a molecule? What is an atom? And what is a compound? Okay, so let's talk about that a little bit. element. Element are the atoms that you have on the periodic table when they're in their natural state, okay? An atom is the simplest form of the element, right? And I'm kind of doing it circular. So basically, I can't break down an atom to a smaller part. One carbon is one atom, okay? One oxygen is an atom. One nitrogen is an atom. Those are an individual atom, okay? Now, an element, it can be one, some cases it can be two, in some cases it can be poly, right? It's whatever the natural state is, what you find it in nature. So let me tell you about the ones that are different. The majority of the elements on the periodic table are monoatomic, meaning one atom, right? So let's take a look at the periodic table again. Okay, so you guys see my periodic table here?
Yep.
Okay, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These guys are diatomic. So in nature, they have to be paired up. Di meaning two. So it's H2, N2, O2, F2, Cl2, Br2, okay? The way I remember it is have no fear of ice cold beer. Have hydrogen, no fear, nitrogen, fluorine, of oxygen, iodine, ice, coal, Cl, beer. Piece of cake. Put this in the anagram order there.
What's up?
Okay, have no fear of ice cold beer. Simple. Or you could just remember H7. Because it forms a 7. Okay? So those are your diatomic molecules. I mean, diatomic elements. So when you see them written in chemical formulas and we're talking about hydrogen gas, it's always going to be H2. If we're talking about oxygen gas, it's always going to be O2. If we're talking about fluorine gas, it's going to be F2. Okay, now when they're in compounds, they don't have to be diatomic. So if we're talking about carbon monoxide, that's just CO, right? If I'm talking about carbon dioxide, that's CO2. Okay, simple. Okay, so there are two other elements that are polyatomic, meaning that they can exist in their natural state can be more than 2, essentially. And that's phosphorus and sulfur. Sulfur, its natural state is S8. And phosphorus, its natural state is P4. I usually don't pick on you too much with it, but you should know it because you may come across it. But usually I'm lax in this area because phosphorus is kind of weird. Majority of it is P4, but then there's just some cases where it will be P. And so it is kind of weird in that sense. And sulfur, the majority of it is S8. Very little of it is just S, but there's a tendency of people forgetting the fact that it is polyatomic. So questions, concerns? Cash. You got it? Good. Okay, so let's keep moving forward then. Okay, so here's hard questions. You know the difference between physical and chemical reactions. You get to tell me in A, is this a chemical reaction? Is it a physical reaction? Or is it both?
Chemical?
Oh,
Both? Both.
Both.
Okay, I'll let you guys vote.
I didn't get up yet. He's still sleeping. It's 8:30.
He's fine.
Okay, put your vote in. Everybody vote. Don't be scared. It's okay to be wrong. You want to be wrong here. You don't want to be wrong on the test.
It's 338, Mom.
Oh, man.
Mommy. Mom. 338. 338. 338. It's 338. No.
Okay, so there's 3 people who haven't voted.
8.
Okay. Come on, you don't have to stand on my shoulder.
Un más, un más.
I didn't get the poll. I don't know. I can't. It didn't give me an option. I don't.
It doesn't give you an option. Okay, so tell me who you're voting for.
I'll just do both.
You're going to say both?
Yeah.
Okay. The correct answer is it's a chemical reaction. Think about what you're getting out of it. At the end of the day, you have this nice, beautiful log. And then after you've done it, it's broken down to, it's broken down to coal or a charcoal and water and CO2 actually. So it's a little bit of both.
So excuse me, the charcoal, we're gonna call it as carbon. The charcoal that will come out from the.
Yes, so it'll actually make that coal part. So that coal is just carbon.
Okay. Yeah.
So the log is just going to be basically that ash that you've gotten from that coal, and it's going to be carbon dioxide, and it's also going to be water, the steam that's going to be coming off that we don't really recognize. Okay. Now, what about B? I'm going to relaunch the poll. Instead of saying A, it's B. So, ice melting.
Melting is physical reaction.
Okay. We have 3 more people. Okay. Ms. Perez, give me your vote.
Oh, I said physical.
Okay. So we'll go ahead and end our poll. So the correct answer is physical, right? Because we're not changing the chemical structure of water. It's still H2O. I mean, or changing the physical or the chemical structure of ice. It's still H2O, right? Now, what about the last one, the glow stick? Put your vote in. Okay, there is something going on. Okay, did you get it? Did it work? Okay, so the correct answer is a chemical reaction. The outside of a glow stick is actually water. Inside is a chemical that will actually react. It's typically an epoxy. As soon as you bust it open, it'll actually cause a chemical reaction to occur. That's how you get the fluorescence. And then as it continues to go, the chemical compound is actually broken down to another form. And then you end up with peroxide and I can't remember the other chemical compound, but that's it. Simple.
Yeah.
And you guys see that. So one way that you can determine whether it's a chemical reaction or chemical properties is if you get energy generated, like for instance, the burning of the log, it got hot, right? So if you stand next to logs that are burning, doesn't it get warm? Doesn't it get hot?
Yeah.
Okay. So if there is a change in temperature or heat, usually is a sign of a, and not always, but is usually a sign of a chemical reaction, right? Another way is an odor. Another way is light or steam or gas coming off of something, okay? But not always, because we know that if there is a change in, if there's a change in the phase, right? Because ice is cold, right? And then if we go to water, that's a little warmer. And if we go to steam, that's really warm, right? So not always in terms of that temperature aspect of things, okay? Okay, so pure or mixture. So we've talked about sugar. CNH, pure cane sugar from Hawaii. So is that pure or is that not pure? Or is it a mixture? What is a mixture?
Or you mix 2 things together.
It's when you mix 2 things together, right? So there's 2 pure substances, at least 2 pure substances that are mixed together, right? Kind of like a cocktail. Yeah? No? Okay, it's gonna be a rough morning, huh? Okay, so a pure substance is what then?
it only has one one kind of matter?
It only has one type of matter. So the thing that's in there is exactly the same throughout the entire thing, all right? Okay, so is sugar pure?
Yes.
Yes, yes, sugar is pure. Okay, because it's only C12H22O11. Okay, so it's pure. Okay, so I'm going to ask you a question. Okay, I have sugar here. Okay, so this here, is it pure?
Yes.
Yeah.
Yes.
I have salt here. Is that pure?
Yeah.
Yeah.
Yes.
Salt? Salt and sugar.
Mixture.
Mixture.
Is that pure?
No.
No.
Mixture.
Oh, it's a mixture.
Okay,
Mixture.
it's a mixture. Okay, so now this mixture here, can you tell the difference between the salt and the sugar?
No.
No.
Could you pick it out and say, okay, yeah, that's salt, that's sugar, that's salt, that's sugar? You can't do that? Okay, so this mixture is called homogeneous. Let me write that on the board. Homogeneous or homogeneous. So we homogeneous because it's the same throughout the entire thing. It's uniform. Okay. So if I had salt and pepper and I mix those two together, then what happens? Is that homogeneous?
No.
Yes.
No, you can see the difference.
You can see the difference, right? It's not homogeneous, right? Because pepper is black and salt is white. So if I mix them together, I have black particles and white particles. So I can see the difference between that. That's called heterogeneous. Okay, see the difference? Okay, so let's say I'm making a cocktail.
So this guy is available because
I have my peach brandy here.
1 hour here I'm gonna come back.
Peach brandy. Peach brandy. And I add water to it. Is that going to be homogeneous or heterogeneous?
Homogeneous, because you can't see the actual water compared to the brandy.
Okay, so you're right, homogeneous. So you can't tell the difference between the water and the brandy in there, can you?
No, it just looks lighter.
Okay, good job. Now, if I add my sugar and salt to my brandy, can you tell the difference?
Yes.
So is that homogeneous or heterogeneous?
Heterogeneous.
Okay, simple.
What if it's dissolved?
Then it becomes
Homogeneous.
It becomes homogeneous. So, yeah, I put extra in there so it wouldn't dissolve on purpose. That's a good question. Okay, simple, no problem, piece of cake. Good. Okay, so how many of you guys cook pasta?
Nobody
cooks.
You said pasta?
You did last night?
Pasta, yeah,
Oh,
pasta,
yes, I cook
spaghetti.
pasta.
You know,
I thought you
should
said
I not call this pasta?
Fettuccine.
Okay, so you all you guys cook pasta.
Yes.
Okay,
Yes.
so how do you guys cook pasta?
And water. You boil it in water.
Water.
Boil the water first.
Add garlic.
You put a little bit of oil in the water first, you know.
Yeah.
Oh,
Garlic.
you're fancy.
And salt.
Okay, I see. Okay, so how many of you guys put salt in the water?
I
Yeah,
put
sometimes.
Yeah.
Yes.
Everybody put salt in water? Okay, so why do you put salt in your water?
I've heard it's for flavoring, but I really don't know why.
Doesn't it help it boil faster?
I don't know. I think so.
So, it's some of you guys says it helps it boil faster, right? Okay, so the other reason, and actually that is partially true, it helps it get to that 100-degree mark faster. Okay, so here, this is an example of boiling water. This is boiling water alone. This is boiling water with salt. So we have a solution of salt. In the case of the solution with salt, we've changed the boiling point. So 100 degrees, water boils at 100 degrees Celsius. Now, if we add salt to it, we've changed that boiling point to a higher temperature. So now that water boils at about, in this case, depending on the salt you have, this is about, let's say, 110. Okay, so that means that the water is a lot hotter than it would be in the case of just the water alone, right? Because once it gets to that boiling point, it sits at 100 and then it evaporates, right?
Right.
Once it gets above that. But here, we're keeping the water in the solution still by having those salt molecules. So we've changed that boiling point by 10 degrees roughly by adding salt. So the reason why you actually put salt in your pasta is so that you can get the temperature hot enough so that you can cook the pasta faster and it doesn't really stick together as fast. Okay? And it doesn't get soggy. Anybody like soggy pasta? Yeah, I always throw it out after I do it, and I do it all the time because I forget to add the salt. Okay? So, this here, right? This here, we're messing with the physical properties because boiling point is a physical property for water. Now we're using chemicals, the addition of salt, to sit there and play with those physical properties. Do you understand that? Because at the end of the day, water's still going to be water, and if you boil it out, water's going to be by itself. And if we boil it long enough, we'll get that salt back at the bottom, right? Have you guys overboiled the water for your pasta? Again, I do this all the time. I'm a professional at overboiling stuff or burning pots, as my mom would say. Okay, so we've talked about mixed. So if I have a pure substance, we have pure, in this case, bromine, and we have pure water. If we mix it together, is that heterogeneous, homogeneous? Is it a mixture? It's a mixture. Is it hetero or homo?
It's a mixture. It's gonna be.
It depends on how much.
Well, are you going to be able to distinguish between the water and the bromine?
The water, because water is clear.
Water's clear. So is this uniform? Is this hetero or homo? Can you tell? Can you see the difference between the water molecule and the...
No.
No, you can't.
There's no difference, so it's gonna be homo.
That's right. It's going to be homo, but it's still, we know that it's still a mixture, right? We know that there's water molecules and there's bromine molecules in there, okay? So both of those molecules are still there because they're not chemically reacting with each other. Okay, so we've already talked about this. You got it? I'll go ahead and misspell homogeneous and heterogeneous. I forgot the E. So this is another example, you know, alcohol, which we kind of did already. Alcohol and water, same concept, right? Okay, another example here is iron and sulfur. So if we have iron and sulfur mixed, let's take a step back. So with alcohol and water, how many of you guys are bootleggers? Any bootleggers here? Okay,
Yes.
good. So I get to corrupt you. Is that what you're telling me? So I make homemade wine and occasionally homemade liquor. Now, the way that you actually make liquor, how do you make alcohol more concentrated?
Let it sit longer, maybe?
Boil it.
Boil it.
Boil it. That's right. We call that process of boiling it distillation, because what we're doing, we're actually distilling the alcohol and the water. Alcohol boils at 87.9 degrees and water boils at 100 degrees Celsius, right? So by doing that, we can sit there and separate the two. If we get it exactly at that 87.9 degrees and we make sure that the system is set up right so we don't blow up the house, right? Or wherever you're living, then you can boil off the alcohol and collect the alcohol by cooling it down after it forms that gas into another tube. And the gas is going to rise and slip into the other tube, and you just cool it down, and then you're able to collect the alcohol. The alcohol will be pure. In some cases, you'll get some bad stuff. You have to run that off first. It'll run off the first batch. But the good stuff will actually last a little bit later, come out later, and come out pretty well. So that's basically how you go from, you know, beer to whiskey in a sense. So the fermentation process only brings alcohol to roughly at most 20%. So if you want that 40%, you have to do distillation to separate the two. So is that using a physical characteristic or is that using a chemical characteristic of alcohol and water?
Physical.
It is a physical characteristic. That's correct. So you're using the fact that the boiling point has changed between the two. The water's still going to be the same, and the alcohol is still going to be the same. Okay? So in the case of the iron, we have iron and sulfur mixed together. So we can use the physical characteristics of iron. Iron binds to magnets, where sulfur doesn't. So if I run a magnet over this sulfur iron mixture, I'm able to collect all of the iron. So is that using a physical characteristic or is that using a chemical characteristic?
Physical?
Physical.
And it's a physical, because we know that iron binds to the magnet, right? Okay, so ways to separate mixtures. So we can use our knowledge. So we can use methods like distillation to separate mixtures. We can use filtration. Filtration is the process of putting a filter. Do you guys make coffee? Anybody make coffee? Yeah?
I do. Yeah.
So do you just put the coffee into the brewer and then you drink the coffee with the coffee grinds?
No.
No, right? What do? You put a filter in there, right? And so that filter keeps the coffee grinds from getting into the coffee. So you could just, you have the coffee. Okay? So you can use that process in chemistry as well. So you can collect solids by using filtration. I'll show you an example. This is the distillation column. This is a filtration system. So basically we have a filter paper. We put the filter paper in a funnel. Here we have a mixture of solids and liquids. So then now we're able to collect the solids in the filter paper and we collect the homogeneous liquid down here. So just like we do with coffee. Piece of cake? Simple?
Yeah.
Not too hard? Fabian, you have that look. Is this boring?
No.
No? Okay, so are we using physical characteristics or are we using chemical characteristics in this case?
Be physical.
Physical.
That's right. It's going to be physical. We know that one of them is a solid and the other one is a liquid. Damn, physical. That's it. Piece of cake, right? Okay, so we've talked about elements. We've talked about molecules. Well, not really. Okay, so an element, as I told you, is going to be that pure substance, right? So it's O2, N2, right? Or it's just Na. A compound is two or more different atoms, okay? A molecule is just two or more atoms. Okay, compound, two or more different atoms. Molecule, two or more atoms. Okay, you guys got that? So let's see what you guys can do. So if I have okay, N2, is that an atom? I mean, sorry, is it atom, element, compound, or molecule, or multiple things? And if it's multiple things, you got to tell me what multiple things they are.
Is it a molecule?
An element.
Okay, we have an element. I hear that. Okay, anything else? I know some other people said something, but it all kind of came out. Blah, blah, blah.
Molecule.
Molecule, okay. Anything else?
An atom. Because it's a diatomic element, maybe?
It's a diatomic element, but that doesn't mean that it's an atom. An atom would just be nitrogen. Do you see the difference?
Yeah.
Okay, so what about, so the answer would be element and molecule. What about CO?
A compound.
Compound? Is that it? So compound is correct. Anything else? Is it a molecule?
Yeah.
Miguel, you're nodding yes. Or is that bobblehead? You're nodding, you're shaking no now? You're on mute, so.
I just moved my head.
You just moved your head?
Yeah.
Is it element?
Isn't it two?
You said it's two elements.
Yeah, I mean, they're both capital, aren't they?
Yeah, they're both capital, so it's two atoms.
Oh.
So is it a molecule?
Yeah, it's a molecule.
Yeah, it'll be a molecule.
It would be a molecule. What about CO? So CO, I mean, capital C, capital O, right? That's a compound and a molecule. Now, what about capital C, lowercase o?
Element.
Is it an element? Is it an atom?
Yes.
Yes.
Is it a molecule?
Yes.
No, it's not
No.
two or more.
That's right. It's not a molecule. Is it a compound?
No.
No, because it's not two or more different atoms, right? Okay, what about CaCl? That should be 2.
That would be a compound.
That would be a compound. What about a molecule?
Yes.
Yes.
What about an element?
No.
Okay, what about an atom?
No.
Okay, piece of cake? Okay. Okay, so now that you know that, we can sit there and talk to you about in terms of how you can break things down. So a mixture is going to be separated by physical means, right? And it's going to give you the two compounds that are there, or the two compounds and a pure element, okay? Now, a compound can only be broken down by chemical means, right? To give you your purest forms, okay? So you can understand the difference between a mixture, which is impure, and then a compound, which is pure, right? Okay, so before we get to this point, yeah, I'll keep going. Okay, so this is an example of some pure substances and some impure mixtures, compounds, right? So for instance, baking soda. Baking soda is sodium carbonate, or sodium bicarbonate, which is a compound, okay? Our copper penny, is that a compound, element, or an atom, or a molecule? Is it pure?
I don't think so. Isn't
Copper
it like a
penny?
mixture of copper and something else? Because the old ones were copper and the new ones are more like a mixture of something.
Yeah. So the new ones are an alloy, right? Primarily copper. The majority of it is copper, but there are little impurities. So you're right in the sense that it would technically be a metallic mixture or an alloy. We'll talk about metallic bonds here in a second. So it's not truly a mixture. It'd be more kind of like a compound, but not really at the same time. What about the lead weights?
Is it a mixture?
Well, the little metal that's in the middle, right? That little metal in the middle is actually a brass. And so, yeah, in that case, it'd be a mixture, but the lead itself is actually pure lead.
Right, okay.
So, what about the copper wire?
Element.
Element, okay. What about 24 karat gold, my gold bracelets?
Element.
Element.
Element, okay. So simple, not too hard. Okay, so you're now familiar with elements. You know how to distinguish elements. You know it could be those two letters. It could be a single letter or two letters, capital, lowercase. Okay, we've talked about the chemical formulas. Okay, so now when we talk about the chemical formulas, that is lower, that's called subscript. It has H2, right? That tells us how many of that particular that particular atom that we have. So in this case, for hydrogen gas, we have 2 hydrogens. In the case of water, how many hydrogens do we have? How many oxygens?
1.
Okay. Oops. Okay. C6H12O6. How many carbons do we have?
6.
6.
How many hydrogens do we have?
12.
How many oxygens do we have?
6.
Okay. You guys got it? So let's see.
Is the flag of the United States of America. Through the republic for which it stands.
Okay, when we have the parentheses makes reference to how many of the molecule or the compound that you have inside the parentheses. So I have, this guy's called ammonium. So in this case, I have 3 ammonium molecules. Okay, so how many total nitrogens would I have in this case?
4.
3.
3. So I have 3 nitrogens. How many hydrogens?
12.
4 hydrogens.
12.
You said, sorry, 12 hydrogens. There you go. And then how many phosphorus do I have?
1.
1.
Okay. Piece of cake? Okay, good.
Oh, sorry.
Okay. Okay, so this kind of gets us to the law of definite proportions. So when we're talking about CO, versus CO2, are these guys different?
Yeah.
Yes.
So yeah, they're different because we have 1 carbon here, 1 oxygen here. Here we have 1 carbon and 2 oxygens. So if we looked at the mass proportion between the two, this would be a 1-to-1 mass proportion to each other. This guy would be a 1-to-2 mass proportion to each other. Okay, you guys get that?
Yeah.
Okay, and that's basically what the law of definite composition means, or the law of constant composition. Okay, so let's talk about what makes up an atom. So an atom is composed of 3 components, 3 subatomic particles. One is called a proton. One is called an electron. And one is called a neutron. Protons are positively charged. That's why you get that P, protons, positively charged. Electrons are negatively charged. And what do you guys think about neutrons?
They're neutral.
Neutral.
They're neutral. Which I like putting a big fat 0 there. Okay. Okay, so let's go to our periodic table. And by the way, your periodic table can be found in your resources under modules at the very bottom of the page. There's a PDF of a periodic table for you. If you want to print it out, I strongly recommend that you print it out. Okay, so the top number here, that 1 up top, that's called your atomic number. Your atomic number defines the atom that we're talking about. And it also equals the number of protons. So carbon has how many protons?
6.
Okay, carbon has 6 protons. Okay, so every atom on the periodic table or element is going to be neutral in charge. What is the charge on protons?
Positive.
Positive. Okay, so a proton is positive. Now, if it has to be neutral, how many electrons must carbon have?
6.
Okay, so carbon has 6 protons. Six electrons. Okay, now this number here is called the atomic mass. So that just gives us the mass of the atom that we're working with. So carbon has an atomic mass of 12.011. Now, the mass number is just equal to the whole number for the atomic mass. So that basically means that we want to round, right? So if we have 12.011, can we round that to a whole number?
12.
12. So the mass number for carbon is 12. Just going to use the symbol for number because I'm lazy. Okay, so the mass number is also equal to the number of protons and neutrons. Okay, so if the mass number is 12 for carbon, and we know that carbon has how many protons?
6.
Then how many neutrons must carbon have?
6.01.
Okay, so who said 6.01?
Me?
Okay, Mandy. So if I cut you up, are you a whole person?
No.
No. So a mass number has to be a whole number, right?
Mhm.
And also, can you have 0.01 of a neutron?
No.
No, because we can't break it down to anything smaller. Okay, so how many neutrons must it have?
6.
6. Yes. So if the mass number is 12, 6 plus 6 equals 12, right? Piece of cake?
Yeah.
Okay, let's see. Chromium. Tell me, how many protons does it have? How many electrons does it have? And how many neutrons does it have?
Which one?
Chromium.
24 protons.
Okay, so we have 24 protons. So what is the symbol for chromium? To help those people who are struggling?
Capital C, lowercase r.
Okay. And so protons, I'm just going to put a P plus. So how many protons do we have?
24.
24. How many electrons?
24.
24. And how many neutrons?
Gonna
It'd be
be
28.
You can round that to 52.
Okay, we round it to 52. So 52 minus 24.
28.
Piece of cake?
Hmm?
Okay, good. Do you want to try one more before we move on?
Yeah.
Okay, let's see. Let's do hydrogen. Oops, I gave you the symbol already. What is the symbol for hydrogen?
H.
Okay, how many protons does it have?
1.
1.
How many electrons?
1.
1.
And how many neutrons?
1.
So you're telling me 1 plus 1
0.
equals 1?
Oh my God.
Oh,
No,
wait,
it's
no.
2. No, it's 0. Okay.
For some reason, every student always does that. It's a given. Okay? Piece of cake, simple, not too hard. Yes, no, maybe. Ready to move on?
Yeah.
Yeah.
Okay. Okay. So now the thing is that we're playing with electrostatic forces here, right? Positive, negative. Okay, Mrs. Perez and Mr. Well, Jonathan, because I can't see your last name, Mathis. Mr. Mathis, since you guys are a couple, right? Which one of you is positive and which one of you are negative?
I'm positive she's negative.
Okay, see? Okay, so they've just validated that there is a positive and negative in every relationship, and that's why you're attracted to each other. So we know that opposite forces, that positive, that negative, they're going to come together, right? And they're going to be attracted to each other, okay? Where two positives, what's going to happen in that case?
Repel each other.
They're going to repel each other, okay? So with electrostatic forces, you're going to have two positives coming together, they're going to repel. If you have two negatives coming together, what's going to happen in that case?
They're going to repel?
They're going to repel. The only time that it's going to come together and stick together if it's a positive and negative. So just like when you're in high school and your mom kept telling you, don't date that bad boy, what did you do? You dated that bad boy. Or don't date that bad girl. What did you do? You dated that bad girl, right? Because opposites attract. Okay? Okay, and this is just basically showing you that, right? So we charged up the silk cloth, then we transferred the charge to both of the cloth balls, and as a result, when they came together, they repelled each other, hence the spacing. So if we charge them up again, and then we touch one of them, then one loses its charge, and then it's attracted to each other. Okay, so let's talk about chemical formulas. Okay, so when we talk about chemical formulas, we've already talked about reactants and products. You guys remember that?
Yeah.
So this line here means yield or make, right? So it means that we're making these products, okay? So the numbers in front represents the coefficient, okay? So that tells us how many of the molecules that we have. Now, every chemical equation needs to be balanced, okay? And the way that we would go about balancing is by paying attention to the law of conservation. The law of conservation says that what you put in, you must get out. So here, I have how many hydrogens on this side?
4.
4. And how many oxygens?
2.
Okay. On this side, how many hydrogens do I have?
4.
And how many oxygens?
Equals 100.
Okay. So this plus means I have 2 hydrogen gases and I have 2 oxygen. So the plus is kind of like an and. They're 2 separate. Okay. So is it true that what I put in is what I got out? I put in 4 hydrogens, I got out 4 hydrogens. If I put in 2 oxygens, I got out 2 oxygens. Okay? So that's basically the law of conservation of matter. Okay? You have that look, Brittany.
I'm just looking. I was just looking.
Okay.
Like, okay.
So you guys want to give a shot? See if you can balance an equation. So the goal is every chemical equation has to be balanced. The very first thing that you have to do is make sure that you have the chemical components, right? So let's say, for instance, how many of you guys eat?
Everybody.
Oh, none of you guys eat?
Everybody.
I would hope that you all eat, right?
Every day.
Okay, every day. I would hope so, right? Otherwise, there's
by
some
now.
issues going on there. Okay, so when you eat, we go through a process called cellular respiration, right? And that's basically where we break down glucose. So food's going to be changed to glucose, or we just get glucose in general. Glucose is a form of sugar, C6, H12, O6. And then to help you break down the sugar, you need oxygen. Oxygen plays a crucial role into breaking down our food. So you have to breathe. And if you notice, particularly during Thanksgiving, you do this. You when you're eating, and you have to take that big breath, and right? Especially in Thanksgiving, right? So we definitely need that oxygen. And then what we get is carbon dioxide, because that's what we breathe out, and water. You got to go tinkle a little bit later too, right? Tinkle means pee. Okay? So, what are the chemicals, what are the elements that are in this chemical reaction?
Carbon, hydrogen, and oxygen.
Carbon,
Carbon.
hydrogen, and oxygen. Okay? So, how many carbon are on our reactant side? These are the reactants.
6.
How many hydrogens are on our reactant side?
12.
12.
And how many oxygens are on our reactant side?
8.
8. Good job. So that's 6 plus those 2 over here.
Yeah.
Okay, so now on our product side, how many carbons do we have?
1.
1.
1,
How many hydrogens do we have?
2.
2,
And how many oxygens do we have?
3.
3,
Okay, so I'm gonna ask you a hard question here. Think hard on it. What we put in, is it what we got out?
No.
no,
No, because we have 6 carbons that we're putting in and we're only getting 1 out. So that means that this equation isn't balanced.
Balance. Yeah.
So we need to balance the equation, okay? The way that we would go about balancing the equation is we want to sit there and put coefficients in front of the molecules to try to balance out both sides, okay? So I have 6 carbons here. How can I make it so that I have 6 carbons on my product side?
I put 6 in front of
put
C.
a 6,
Put 6 in front of the C right here. Is that what you're saying?
Yes.
yeah,
Okay. So then if I do that, how many carbons do I have now?
6.
6.
Okay. How many oxygens do I have?
12.
12.
Plus,
1.
that's
Okay,
what,
plus
13. Somebody was talking in. Okay, so now our carbons are balanced. What about our hydrogens? Are they balanced?
No.
Nope. Okay, so how can I balance those hydrogens?
So you gotta put 6 in front of hydrogen to get 12.
Right here?
Yeah, in front of the water.
Okay, in front of the water. Okay, so then that gives me a total of 12 hydrogens. How many oxygens? Altogether.
Altogether, we have
So that's
plus
6 times 2 is what?
12 plus 12, 24.
12 plus 12? 6 times, there's 2 oxygens there? I only see 1 oxygen in water.
8.
So there's 6, so that's 18, right?
15, yeah.
So we have 18 now. Okay, so our carbons are balanced, our hydrogens are balanced, but what about our oxygens? Are they balanced? I have 18 over here and I have 8 over here.
No.
It's not balanced. So, dang, what can I do? So if I come over here, these guys, if I leave them alone, they'll be okay, right? So I want to leave this whole molecule alone. So that means that I have 6 oxygens here. So if I take my 18 minus 6, that gives me 12, right? So what can I put in front of this to make that 12?
6.
6,
Okay, so let's check it to be sure. So 6 times 2 is what?
12.
12 plus the 6 that we have here.
18.
Is it balanced?
Yeah.
So what we put in is what we got out. So that's balancing a chemical equation. Okay. Now, this chemical formula or chemical reaction, it's going to be one that you see in biology over and over and over again. As I told you, it's for cellular respiration. So it's good to kind of remember it so you don't always have to go through and balance it out. So the way I always remember it is sugar's the devil, right? So sugar, glucose, 6, 6, 6. Sugar's the devil. Piece of cake?
Yeah.
Miguel, you have that look.
I'm good.
You're good? Okay. Okay, so do you guys want to try it out a little bit? I know our time is up. But I have like 3 more slides. Actually, it's more than that, but I'm going to pretend like it's 3 more slides. so that you guys are good to go. Okay, actually, it's 5 more slides. Okay, so the law of conservation basically is what you put in is what you get out. Now we also have energy. Energy is just basically the transfer of work. Energy is just the ability to do work or to transfer heat. Okay, so that's how we define energy. And actually, I am going to stop here because I don't want to rush it. So we'll finish this up on Wednesday.